Good morning, everyone. This is Chengxi Zang from Tsinghua University, and my presentation is about the dynamics of how you add friends in social media. The title is Long-Short Memory Process, Modeling Growth Dynamics of Microscopic Social Connectivity. This is a joint work with Peng Cui and Wenwu Zhu from Tsinghua University and Chrysos Fellows from CMU. The growth phenomenon of social network is ubiquitous in both physical society and online social media. For example, the growth of US population, the growth of Facebook, and the growth of WeChat users. The growth phenomenon is very important, has implications for the policies, and also the growth of the WeChat and the growth of the Facebook is directly linked to the stock price with their companies. However, the evolution of social networks like the Facebook and WeChat, which have hundreds of millions of users and billions of links, are driven by the growth of each individual's social connectivity. You add friends, your ego network grows, and this macroscopic social connectivity growth is spatially and temporally aggregated into macro social network growth. Thus, in order to understand the macro social network growth phenomenon, we need to study their macroscopic building blocks. The understanding of the macroscopic social connectivity growth is of vital importance because it can advance our understanding on the universal human dynamics, provide the macroscopic mechanism for social network growth, and lead to a broad range of applications, including clustering, prediction, outlier detection, and so on and so forth. By a data-driven approach, we studied the detailed evolution traces of the largest social network in China, WeChat, from 0 to 300 million users and 4.75 billion friendships, spanning its first 2 years. The dataset explicitly records when, where, and how a link is established, serving as one of the largest datasets for the study of macro growth dynamics. Mathematically, we try to figure out how the number of your friends grow over time. Focus on this. We want to find out what are the patterns of the macro growth of social dynamics and what are the plausible mechanisms governing this macro growth dynamics. And can we propose a unified model to produce the realistic growth dynamics for largely heterogeneous individuals? By investigating the real data, we found the growth dynamics of your number of friends exhibit rich complexities. We showcase 3 individuals' growth dynamics over 2 years. We find a wide range of parallel growth in the long term and stochastic burst in the short term. However, the existing work models on network evolution found the sublinear growth, like the BA model and the fitness models. They are based on some mean field assumptions, and they ignore the densifications. And the linear models and the superlinear models, they are both in the mean field manners. As a result, we have no understanding on how individuals' connectivity grows in the social networks. All existing models failed against with observations we observed in the real data. So far, we found 2 growth patterns in real world: the long-term parallel growth, or various parallel growth, and the short-term stochastic burst. And previous models failed. Thus, we want to know the mechanisms governing the observed patterns. We need a unified model to generate both the growth patterns. So let me elaborate on the mechanisms and then propose a unified model. The first mechanism is a kind of long-term memory. We name it average memory effect. The intuition is as following. The behavior at present is influenced by the whole history in an average manner, which is modeled by the rating of making friends at present is proportional to the average rate of making friends so far, just highlighted in red, and which can generate the parallel growth, which is proven by the equations in the lower panel. The second mechanism is kind of short-term memory. We name it multiscale memory effect. The intuition is as following. Memory fades due to the mere passage of time since last event. But how does the memory decay? We model the multi-scale memory effect by the inter-event time distribution p tau. An illustration below shows what's the definition of the inter-event time. The axis is a sequence of the event times, and the inter-event time is just the time difference between the consecutive event. The right figure showcases one empirical inter-event time distributions. We found flat short scales, fat-tailed middle scales, and exponential-like long scales. The third mechanism is another kind of short-term memory. We name it correlated memory effect. The intuition is the latest inter-event times are correlated rather than independent. Mathematically, the joint distribution of the consecutive two inter-event time is not equal to the product of the two marginal distributions. And imagine there is a sequence of inter-event times. You just arrange them. You set the small values together and followed by the large values. Then it can generate burst, which means thus the correlation between the IETs can also generate a burst. Based fundamentally on the three memory effects we proposed the long-short memory process, LSMP. We follow the temporal point size framework by modeling the hazard rate. The hazard rate describes the rate of the occurrence of the event, given the whole history of the previous event. The hazard rate of the long-short memory process has two parts, indicated by the name, long-term memory part and the short-term memory part, respectively. Let me elaborate on the hazard rate equations. The average effect in a hazard rate language, namely the present hazard rate is the mean value of its previous hazard rate, which can generate stochastic power law growth with arbitrary exponent alpha. When alpha smaller than 1, it generates decelerating power law growth. When equals to 1, it's just a linear growth. And when it's larger than 1, it's kind of accelerating power law growth, implying a richer phenomenon. The multi-scale inter-event time distribution is also captured by our models. Specifically, lambda 0 and delta 0 controls the bursty short scales. The theta controls the fat-tailed middle scales. When theta equals to 1, it gives rise to a power law decay. Otherwise, when theta not equals to 1, the process generates the stretched exponential decays. You can see our papers for the detailed proofs and why different thetas can generate different decay forms. The second mode is the long-term mode. It's captured by the lambda infinity and delta infinity. The intensive activities followed by the long vacations generate the burst. The correlation of IETs are also captured by our models. When alpha larger than 1, the accelerating growth gives a positive correlation of the IETs. When alpha smaller than 1, the decelerating growth gives negative correlations. The superpositions of the latest amphiphylline kernels gives short-range correlations. The correlations also generate burst. We learned the parameters of our models by maximizing the log likelihood functions. A good advantage is that every parameter of our models has a closed form gradient, so we can adopt a wide range of optimization algorithms. We also design two simulation algorithms of our models. For brevity, we don't talk about the details. We open source the data, and you can refer to the code and the paper to understand the details. All right, so it's about the experiment results. For each individual, we have its real dynamics and generated dynamics. So we'll first validate whether the fitting results of our models is good or not. We set 3 checkpoints: the growth shape curves, like the first panels, the inter-event time distributions, highlighting the second panel, and the zero correlations. We also consider some most representative baselines for human dynamics modelings: the Poisson process, Hawkes process with different kernels, and the self-feeding process. We compare the mean average errors of the real dynamics and the generated dynamics. As for the error bars, the lower, the better. The proposed models fit the reality much better than the baselines for both the metrics. We then demonstrate that our models capture the multi-scale inter-event time distributions. We test whether the real dynamics and the generated dynamics, they share the same inter-event time distributions. We adopt the two-sample case test for these standard statistical test missions. We conduct tests also on the, on the IET, on the inter-event time and the log transformed IETs. The higher the pass rate, the better. The lower the errors, the better. Our models outperforms all the baselines significantly in both the metrics. We further show that our models capture the correlations between their inter-event times by comparing the joint distributions from the real data and from the generated data. Again, we adopt the two-dimensional case test to the joint distributions, and again, our models base all the baselines. What's more, we compare our models, we compare the inter-event time distributions by the log transfer form and the shuffle forms. We can see that the log transfer form gives a consistent result. And by shuffle the inter-event times, we can find our models give us the largest marginal increase for the pass rate, which shows that our models capture their correlations much better than others. One good advantage of our model is that our modeling parameters all have very clear physical meanings. Thus, by analyzing the parameter space, we found some statistical regularities of the human dynamics in making friends. In the long term, we plot the exponential exponent distribution in the figure A. We found it shows a large heterogeneity in power law growth. We can find sublinear, linear, superlinear growth, and it spans a large range. And for the average rate, we can find that it shows a mixture of the Gaussian models, and it spans eight order of magnitude from per second to per year, which captures different activities of different users in making friends. And the third plot plots the time scale of making friends. It shows the 4 days, and it's a skewed log-normal distributions. 4 days have some explanations. Say you find a new job at the Monday, and 4 days later, you add all the friends in your lab or all the groups, so the scale is just 4 days. So one Monday add 4 days Friday. For the statistical regularity for the human dynamics in the short term, we find some Gaussian mixture distribution of the Fizzling exponent theta. When theta equals to 1, it is exactly the power law decay. But we found rather than the pure power law decays, theta not equals to 1 is more general, indicating a stretched exponential decay. We also find the bimodal distribution for other short-term parameters like the scale and the rate. Due to the prevalence of the normal distributions and its variants, like the scale normal, log normal, and their combinations, in empirical data, we apply the Gaussian mixture models to their parameter space. We want to find some clusters, and at the same time, we found some outliers. For example, so we can see the outlier guys, they add few friends within his first year and add a lot of friends within hours. We found these outlier behaviors are majorly money-driven, like this. So this guy probably post a lot of advertisement in his moment, and his friends will buy this and get influence from this advertisement. So it's behavior like an outlier. The same clustering experiments can conduct in the short-term memory space. We found people in the upper clusters in figure A whose IET distribution shows a very clear flat short scales, which captures adding friends at a very fine-grained gradualities, because WeChat propose some functionality to add friends within minutes. Like the shake it, you can shake it, add a lot of friends, so you have a very flat short scales. Furthermore, we test the dependency between the long-term and the short-term, whether we can divide them. And we plot their parameters, theta, and the alpha is the power law exponent, and theta is the decay. We found, given the theta, we can find a larger variance, so it shows little correlations. All right, let me conclude. We studied the growth dynamics of the individual social connectivity. We found 2 growth patterns, long-term parallel growth and short-term bursty growth, stochastic bursty growth. And we proposed 3 memory effects: average memory effect, multiscale memory effect, and correlated memory effect. And based on these mechanisms, we propose a model named long-short memory process, which has parsimonious parameters, and each parameter has very clear physical meanings. And it's easy for optimization to learn the parameters. And our models did well in fitting the realities. And also, it's useful for many human dynamics, like we can fit the growth curves. At the same time, we can fit the decay memories. We can do the clusterings. We can do the pattern mining in the parameter space. We can do some outlier detection and prediction the future growth of your neighborhoods. We just publish our data here for reproducibility. And thanks, that's all.